All right, lesson 6, dividing by x minus a and x plus a. Today we're working really hard to observe patterns when we divide certain types of polynomials and make some generalizations to help us quickly compute quotients without having to do the work involved with the reverse tabular method or the long division method. So today is really wrapping everything together, and we need to work really hard at trying to recognize some patterns to make our lives easier. The opening exercises. These are all division problems, but what we want to do here is recognize some patterns. So the instructions say to work these out on your own and work with a partner, but I'm just going to point out some patterns to you so that you can log them in the back of your mind and try to remember them. On the top here, we have a difference of two squares, which works out to x plus 3 and x minus 3 over x minus 3. Okay, we know we can cancel, and we're left with x plus 3. Okay, these are things that you actually could do in your mind. You can go straight from here to there. In the long term, I wouldn't necessarily recommend it. I would go ahead and write this out and then cancel and then write your answer out. But you do not have to do, the long division. Excuse me. You do not have to do the tabular method. That is work that should be unnecessary as you recognize patterns and quickly work through your work. Here we have, this next one, we have the difference of cubes. So we can work that out into x minus 3 and then x squared plus 3x plus 9. We learned that a few lessons ago, over x minus 3. And then we are with an answer. And this last one is really the difference of squares twice, which is sort of funny. X squared plus 9 and x squared minus 9 on the top. But here we have the difference of two squares again. So x squared plus 9 and x plus 3, x minus 3 over x minus 3. On this last one, we have another pattern where we can set this up as x minus 3. And then we're going to do that fun little pattern where we reduce our power, x squared y squared plus xy cubed. That's not right. Okay, this last one, it's a pattern we learned about a few lessons ago, and it's a really important one to remember because you can really save yourself a lot of time. We can do x minus 3, and then you have your a and your b term. We go down by powers for the first term and up by powers for the second term. So a 3, a 9, and then a 27. All over x minus 3. So we have our answer here. Okay, do you see how that's so much faster than long division if you can recognize your patterns? All right, so this is what we just did. It's what I just talked about. I did not model both ways. I looked for patterns. And that's really what you want to do. It's going to save you time and it's going to help your accuracy. Okay, what patterns did we notice in the opening exercise? Use the patterns we've observed to determine the quotient. Explain your reasoning. Okay, here I see x to the 5th. I don't know what 243 is, but I'm just going to do a little test. I'm going to see what the 5th root of 243 is. Okay, I'm going to punch that into my calculator, and I see that that equals 3. So I know that I'm going to cancel that out by doing an x minus 3. on the top of my fraction bar, x minus 3. And then I can use that pattern that we actually just did with the third question on the previous slide and go through our a and b terms, our x and y terms, to come up with a long polynomial. I reduce that first term by 1. I'm doing all pluses here. Okay, the second term is going to be 3x to the third. That would be 3 to the first power, 3 to the second power, and reduce your x by 1. 3 to the third power. I said 3, I wrote 3. I did not mean to write 3. 27x, and then fourth power I think is 81. I'm going to check that because I hate to make a mistake. Yep, 81. All over x minus 3. And we have our answer. Okay, we don't need to test our conjecture because we did our conjecture and we figured it out, and we actually looked at it on the last problem, which was a lot of fun. Okay, exercise 1. Use the patterns to predict each quotient. Explain how you arrived at your prediction, then test it by applying the reverse tabular method. You guys are good, okay? I don't need you to do work just to do work. We know what we're doing here. This first one is difference of squares, x plus 12, x minus 12 over x minus 12. And we have our awesome answer. Okay, I think no, we didn't do this one. We did one just like this one, though. I have difference of cubes, but we actually don't use difference of cubes here. We use the pattern that we just used on the previous slide. I know I want x minus 2 first, and then I reduce that term, or sorry, you reduce the power, and I reduce the power. So we have x squared plus our cubed root of 8. Oh goodness. Our cubed root of 8 is 2. So 2 to the first power, 2 squared, all over x minus 2. So we look for a pattern. And then do the math. And I'm actually going to show you the patterns on another slide. Hold on. Okay. Okay, this is important. I would make sure you have this written down somewhere. When you have x to the n minus a to the n over x minus a, that gives you x to the n minus 1 plus a x to the n minus 2. Really out front here you have an a to the 0, which is a 1. That'll keep your pattern alive if you want to make sure that's included in your head. A times x to the n minus 2 plus a squared x to the n minus 3 plus any amount of terms you want, a to the n minus 2x plus a to the n minus 1 x to the 0. And if you see, this x to the 0 matches the pattern with that a to the 0, so it totally makes sense. But if you had a x to the n minus a to the n over x plus a, your pattern's a little bit different. And we're actually going to do that with the next set of exercises. Okay, this first set deals more with dividing by x minus a. Alright, again, we're still doing x minus a. Use the patterns to predict each quotient, explain how you arrived at your prediction, and then test it by applying the reverse tabular method. Go ahead and give me a quick explanation if you're not showing your work. I'm going to push pause though. I expect you to push pause too. With both of these problems, I used the pattern I showed you on the previous slide. The cube root of 125 is 5. 5 times 5 is 25. Times 5 is 125. Here we have, the sixth root of 1 is 6. Sorry, is 1. That's hilarious. Those are the things I usually delete when I say something silly like that. And I wrote it again. Did you guys see that? The sixth root of 1 is definitely 1. So I'm dividing by x minus 1. Here, there's 1's as your a term for every single one of these. Okay, example 1. What is the quotient? Use the reverse tabular method or long division. Okay, don't worry about it. We're going to do x minus a. Actually, it's x plus a. Okay, this is the difference of 2 squared. Oops. X plus a, x minus a, and we're dividing it by x minus a. All right. Find the following quotients. Okay, I'm going to go ahead and push pause. You guys got this now. There you go. I don't have any work to show because I used the pattern. Oops, sorry about that. I used the pattern that I showed you 2 slides ago, and just used my exponents to figure out my answer. Okay, what patterns do you notice in the quotient? How do these patterns compare to the ones you observed in the opening exercises? How can you rewrite these division problems as multiplication problems? So what patterns do you notice in the quotient? The terms are always added, and each term is a product of a power of x and a power of a. That means the terms are always added. That's where we did, x to the n plus, so they're always added, a x to the n, so this is n minus 1, n minus 2, etc. So the terms are always added, which is right here, and each term is a product of a power of, if we're doing x minus a, each term is a product of the x and the a. As the powers of x decrease by 1 for each consecutive term, the powers of a increases by 1. And that's what I've been showing you with each example. How do these patterns compare to the ones you observed in the opening exercise? Well, in the opening exercise, we actually started looking at these patterns, so we didn't do the long division. We started looking at them probably early. How can you rewrite these division problems as multiplication problems? Well, first of all, if we have, let's just say x cubed minus a cubed, that equals x minus a, x squared plus ax plus a. We have been skipping this part on purpose only because we're dividing by x minus a. So there's really no need to write it. Makes sense? We're just making our life a little bit easier. To give you another example, if I had to the 4th power, that would give me x minus a, x to the cubed, plus ax squared, plus a squared x plus a. And what we've been doing is dividing by this, which gets rid of those. Continuing on, we just spent our time doing x minus a. We are not shifting our focus to dividing. We are now shifting our focus to dividing by x plus a. Okay, what we're going to learn right now is For instance, the difference of two squares will divide correctly by x plus a without a remainder. The difference of two cubes, that's a cubed minus a cubed, will not divide by x plus a without a remainder. Okay, that doesn't work. X plus a does divide without a remainder into the sum of two cubes. So if I have, sorry, turned off my pen, x cubed plus a cubed over x plus a. Okay, I can do this one with no remainder, and we'll show you how. Okay, the point of this second half of the lesson is that some of our division problems form remainders, and that's not what we're interested in this lesson. We're more interested in the ones that do not have remainders because we're looking at identities. We're looking at patterns that these polynomials form. Okay, so let's go ahead and try a few. I said that the difference of cubes divided by x plus a doesn't work. So let's go back forward. Predict without performing division whether or not the divisor will divide into the dividend without a remainder for the following problems. If so, find the quotient, then check your answer. So I just said if you have the difference of squares and you're dividing by x plus a, that yes, it will work. Okay, I'm going to factor and divide. And I'm left with an answer and no remainder. Okay? Here I have the difference of cubes divided by x plus a. I'm going to go back a slide. So here I have the difference of cubes divided by x plus a. Predict. If so, find the quotient, then check the answer. This one isn't going to work, and I'll show you somewhat quickly. X cubed minus a cubed factors out into x squared plus ax plus a squared over x plus a. I cannot factor this one any further, and these don't cancel. So if I did the long division, that wouldn't work. So here we're going to say no. Okay, x squared plus a squared divided by x plus a. I can't factor this. So we're going to say no. X plus a is not a factor of x squared plus a squared. Now I have the sum of cubes over x plus a. That does work. This gives me x plus a, x squared minus a squared x plus a. That's wrong. I might have done that wrong on the previous page. There we go. All over x plus a. And that does cancel out. So yes, it does work. Cool. All right, find the quotient for the given problem for n equals 2, 3, 4, and 8. Just pointing out, no matter what we make n here, this is going to be a perfect root of it. I mean, if it's n squared, I can take the square root of 1 and get 1. If it's n to the 8th power, I can take the 8th root of 1 and get 1. So this really is a problem like we've been working on the whole time. So rather than do the long division, we're going to go ahead and just give the pattern. So for n equals 2, and I need to point out, there's a mistake in the slide. Your classwork is perfectly right, but this should be minus 1. So for n equals 2, we're going to get x to the first power minus 1. Sorry, plus 1. For n equals 3, we're going to reduce that power by 1, squared plus x plus 1. For n equals 4, reduce the power by 1. And for n equals 8, same deal. Reduce the power by 1. Lots of x's. Perfect. Exercise 4. Use your... Oh. Alright, we've used your work in part A to write an expression equivalent to this for any integer n greater than 1. We already have a little bit, so let's just write it down again so we make sure it's in the right spot. We're going to do x to the n minus 1, x to the n minus 2, plus x to the n minus 3, plus many integers as you want. We can say x to the first power plus 1, which is really x to the 0 power. Cool, we've just discovered our pattern. Okay, look at your student handout. You can conclude the statements are true for all real values of x and a. This is important to know. All of these patterns right here. We have the difference of perfect squares, difference of perfect cubes, the sum of perfect cubes, and what those patterns are going to be. It seems the following statement is also an identity for all real values of x and a. So we can do that for all values if it's subtraction. Cool. Good work today.